So, today's lecture is really just going to be about truth tables and what truth tables are, how to use them, and how to interpret them. So to start off with, let's talk about what a truth table even is. Really, at the heart of it, a truth table is just a method of discerning the truth value of a statement. So, it's a little weird way of describing a thing. Let's look at a few of them. The most simple truth table we might have is just a table for P. Just the statement P. That statement can either be true or it can be false. Notice we're not saying it is true and we're not saying it is false. We're looking at each individual case of it being true or false. And in that way, we can think of each row of a truth table as being a set of cases. It's because of this aspect of truth tables that they become so important to the sciences, to math, to everything really. Because what it does is it allows us then to say, all right, this is the general behavior of a truth table given the set of statements that we want to know something about. Because this is the behavior of it, we can now design a set of experiments or tests to discern which particular case we're in, which particular case we're looking at. Now, having said all of that, let's look at a few. Like I said, the most simple case of a truth table would be the table for just the statement P. It's either true or it's false. Now, if we wanted to look at the truth table for the negation of P, we would start by writing out the table for just P. Again, P is just true or false. But the negation of P turns the truth value into the opposite of that. So, the truth table for the negation of P, under that column, the negation of P, we would have false, or we would have true. So again, it's showing us the relationship between one thing and the other thing, and how the truth values interact. Cool. Let's now look at what's called the conjunction. The conjunction, a conjunctive statement, is the statement P and Q. For this truth table, we want to start off by looking at P, and we want another column looking at Q. Well, there's a couple cases we now have to worry about. If P is true, Q could be true. Alternatively, if P is true, Q could be false. If P is false, Q could be true. And if P is false, Q could be false. So we have to consider each of these statements. And then, once we consider each of these statements, we can start filling out the column for P and Q. Well, in this particular case, if P is true and Q is true, the statement P and Q, well, it's going to be true. If P is true and Q is false, the statement P and Q, well, it's going to be false. If P is false and Q is false, well, false and true is still a false statement. And if they're both false, P and Q would also be false. Now for the disjunction, it's a little different. The disjunction is looking at the statement P or Q. And remember, this is the inclusive or. So what we're saying is, if P is true or Q is true, then P or Q would be true. Because one of the two are true in this case. Similarly, if P is true and Q is false, one of them is true. So P or Q is true. False and true, Still, same idea. It's going to come out to be a truth value of true. And if they're both false, P is false or Q is false. So that value comes out to be false. So generally what this is doing is saying, let's compare the truth values of these individual objects, and let's build up to whatever our statement is. Usually it's a compound statement. We almost never use the trivial single statement. It's almost always to evaluate compound statements. But these truth tables are just a way of saying, let's build up to our collective big statement, our major compound statement, and follow how the truth behavior changes all the way through that, and find out what the final truth value for the entire statement is. So again, like I said, we start out by looking at the different possible cases for P and the different possible cases for Q. And then we look at the combinations of them, and we say, all right, based on the different combinations that are possible, these are all the different possible truth values for the statement, in this particular case, P or Q. Similarly, P and Q. Having said that, let's look at a couple more solid examples. So, to start off with our examples, let's consider this truth table behind me. What we're going to be building up to is trying to decide what the possible truth values are given these cases for the statement not P and Q and not P or Q. So, starting off, we know that P can be true, Q could be true. We know P could be true, Q could be false. We know P could be false, Q could be true, or they could both be false. If that's the case, we've already talked about what the truth values are for P and Q. And we've also talked about what the truth values are for P or Q. But what about the negation of P and Q? Well, the negation of P and Q is just the reverse, right? If the statement was true before, it's now false. So forth and so on. So for the negation of the statement P and Q, because that's what we're saying here, right? We're saying P and Q, but not that. Not the statement P and Q. All right, well, if that's the case, then what we're going to have is false, true, true, true. Because it's the opposite, it's flipped. Similarly, for not P or Q, so not the statement P or Q, we're going to have the reverse again. Which is going to come out to be false, 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 true. Now we want to fill out this last column. But notice this last column, all it reduces down to is this case. Let me move out of the way. It reduces down to this case and this case. So, to fill that out, what we're saying is false and false, true and false, true and false, true and true. So to fill it out over here, a false statement and a false statement is still a false statement. A true statement and a false statement is still a false statement. A true statement and a false statement is still a false statement. A true statement and a true statement, well, that's a true statement. So, the truth values, given the combination of cases that we have, could either be false, 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 or true. Again, each one of these rows represent a case of combinations. We have the combinations of P and Q's. We've built up what each of these individual statements mean. And then we've said, let's put them together in a larger statement and figure out what each possible case results in. Having said that, let's look at a couple other examples. Now, for this particular example, what we're going to be doing is we're going to be filling out this truth table. We're going to be using it then to determine the truth values of particular statements, given that we know what the truth values are for each individual statement, for each simple statement. So to begin, what we've got here is the truth table P, Q, not Q, P and Q, P, what's supposed to be or Q. Let me fix that really quick. P or Q, and P and not Q. So let's start off with, we know what the truth value is for Q. So we know what the truth values are then for not Q. For not Q, we're going to have false, true, false, true. Well, we already know what the truth values are for P and Q, P or Q. So let's go ahead and find out what the truth values are for P and not Q. Well, for P and not, my mistake. For P and not Q, we have true, false. Well, true and false is still false. For true and true, well, that's true and true. So it's going to come out to be true. For false and false, it's still going to be false, right? False and false is false. And finally, we have false and true, which is still false. All right, so now, how are we going to use this to answer these particular, to determine rather, these particular truth values? Well, in our first example, we've got P as the statement, 13 is greater than -1. That's a true statement, we know that. All right, cool, we know the truth value of that, true. Let's circle that over here. We're going to be in one of these two cases, right? Well, for Q, the statement is 5 minus 3 is equal to 2. That's also a true statement. So, we know that this particular example is going to be in this case here. All right, cool. If that's the case, the truth value for P and Q, we follow it down, we say P and Q, in this row, that's true. For P or Q, again, true. Okay, cool. Now for this next example, for this next set of examples down here, we've got P as a statement, 3 times 5 is equal to 15. That's true, okay. So we're going to be, again, in one of these two cases. For Q, we've got the statement, 4 is less than 3. That's false. So now we've determined we're in this case. In this case here, the second row. So we now want to know what the truth value is for P and not Q. So we look at the second row, go over, we find P and not Q. That's true. Generally, that's how we're going to use truth tables to determine the value, the truth value, of very particular compound statements. Having said that, let's move on. Now, up to this point, you may be wondering, well, so far we've only had 2 statements. What about when we have more statements? How does that change everything? Well, really, all it changes is the number of rows. And at the end of this example, I'll get to how it changes the number of rows. And I'll also explain a little bit of how I started off this part of the table, right? In the meantime, let's try to use this table up to this point to fill out this particular column here. All right, start off with, we've got the case of P, Q, and R. And what we're trying to answer is going to be what the truth values are given a particular set of cases or circumstances, right? For each case, whatever the particular truth values are. Given that, what is going to be the truth value of the statement P and Q or R? Well, looking at this, you start off by saying P can be true, 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 false, 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 false. Q could be true, true, false, false, true, true, false, false. And R could be true, false, true, false, true, false, true, false. Again, I'll explain how I got to that combination in a minute. If that's the case, then that means the corresponding truth values for P and Q will just be true, true, and then false for the rest of them. Okay. Well, if that's the truth value for P and Q, now we want to look at what the truth value is for the statement P and Q or R. To find that, we've got true or true. It's going to be true. False or true. Well, this is the inclusive or. So one of them is true. Our truth value is also going to be true. True or false. Again, one of them is true, so because it's the inclusive or, we get a truth value of true. False or false is going to give us false. True or false, true. False or false, false. True or false, true. False or false, false. All right, so now we've used everything we've got up to this point to figure out what the possible truth values are given each individual case. How did I come up with this truth table, though? How did I know to start with P, Q, and R in those orders? And how did I know how many rows I was going to need? Well, for each unique statement you have, so for each P, Q, R, S, whatever, you're going to have 2 to that power number of rows. What I mean is we have 3 unique statements, P, Q, and R. We're going to need 2 to the third number of possible rows, so 8 rows. 1, 2, 3, 4, 5, 6, 7, and 8. From there, to start off constructing this, we want to know each possible case. To me, the easiest way to set up this table would be to say, let's consider the first half of our table to be the cases where P is true, the second half to be where P is false. Then, every quarter of the table, we swap. So we go from true, true, false, false for Q. And then for R, we have every row swaps. And in this way, we can consider each and every possible combination. So if we were to have, say, 4 statements in this case, P, Q, R, and S, We would say the first 8 of P are true, the second 8 are false. Well, first we would have 16 rows, because there would be 4 possible statements. So 2 to the 4th would be 16. The first half of that, we would say P is true. Every 4, we would say Q is true. For the next 4, Q is false, and keep flipping it that way. Then every 2, R is true, and then R is false. And then for S, we would have every other row. Now again, the way I knew the number of rows I was going to need is because what I said was the number of variables, or statements I mean, we're going to call that N for right now. So the number of rows then that's going to be 2 to the power of N. Awesome. Having said all of this, let's move on to conditional statements, conditional and biconditional. In our last lecture, we talked a little bit about this connective right here. We said that this is called the if-then connective, also known as the implies connective. As an entire statement, we call this the conditional statement. And its truth table is as follows. If P is true and Q is true, then what we've got here is P implies Q is also true. If P is true and Q is false, then the statement if P then Q is false. If P is false, Q is true, then the statement if P then Q is true. And if P is false and Q is false, then the statement P implies Q is true. Now you might be looking at this saying, hey, wait a minute. This third case seems wonky. You're right, it does. I'm not going to disagree with you on that. It took me by surprise when I was learning this the first time as well. Having said that, there is an example on page 151 related to table 3.16 that I personally thought explained this really well. When I was going through making the lecture notes, I saw it and thought I'd let you all look at it for yourselves because it does really do a good job at explaining why some of these values are what they are, particularly this third row. Again, like I said, when I was first learning it a couple years ago, I looked at it and was like, what? The example that they use does a great job at explaining it. So please, please, please look at that example. Having said that though, we now want to use these truth values to determine what the truth value for Q implies P would be given each of these cases. Well, for Q implies P, we're moving in the opposite direction. To start off with, we've got true implies true. Well, we already knew that was true. Now we've got false implies true. That was that wonky example, and we know that's true. Now we have true implies false, which we know to be false. And finally we have false implies false, which is true. Okay. What about P implies Q and Q implies P? What are those truth values? Well, true and true, False and true, false, true and false, false, true and true, true. So the statement P implies Q and Q implies P has truth values true, false, false, true, given this particular setup for our truth table. Having said that, this particular example is a special case. We call this the biconditional. We oftentimes write it in a particular way. Because this is so long to write, I can't talk now. Because this is so long to write, we oftentimes write it as P implies Q with an arrow pointing in both directions. P implies Q and Q implies P. Having said that, got one last example for us. Now, for this last example, we've got three different statements, P, Q, and R. 2 to the third power is 8. So because we have three different statements, we're going to have 8 different cases to consider. And what we're going to be trying to find out is, given each one of these cases, what's the truth value for the statement not P implies Q and R, and Q and R implies not P. Another way you might hear it stated is not P if and only if Q and R. That's a way mathematicians usually like to say that. Having said that, I went ahead and filled out most of the truth table for us. And what we're trying to do is figure out if these two columns imply each other, right, in both directions. If that's the case, if you I don't know if you caught on in the last example, if that's the case, then they're both going to have the same truth value, right? True implies true, true implies true. So in that case, we have both directions, it would be true, right? And that's what the biconditional is really saying. Are they both the same value, the same truth value? So, knowing that, using that, looking at this first case, false and true, well, that's going to have a truth value of false. False and false, they're both the same. So true, false and false, both the same. Again, true. Again, true. True and true is going to be true. True and false is going to be false. True and false is going to be false. True and false is going to be false. So, what we've done is we've said, using this truth table, figure out what each case of this is going to be, what the truth value for each case of this will be. That's all I've got for y'all in this lecture. If you have any questions, feel free to shoot me an email.